There, folks. I need you guys to stop talking, please.
It just has an automated
All right. So today we're going to be talking about an application of parametric functions. That situation is called projectile motion. Quick show of hands, those of you in a physics class or have taken one. Okay, so a couple of us. Shh. Those of you that have, can you stop talking, please? Thank you. Those of you that have done some physics before, this will look a little bit familiar. Obviously, we're going to approach this in a slightly different fashion. That's a little bit more mathematically rigorous, but you may be familiar with some of the equations and whatnot that we'll use here. So we're going to start by defining some equations. All right, the height s and velocity v of an object in free fall after t seconds are given by the functions. S of t equals 1/2 gt squared plus v naught t plus s naught, and v of t is equal to gt plus v naught. So let's discuss what these letters represent. So what do we suppose G represents here? Great. Those of us in physics, what is the value for gravity? Okay, so nobody's given a correct answer because nobody's included a unit. That's still incorrect. Man, I feel bad for your physics teacher right now. So the value for gravity is negative 9.8 meters per second squared. Why is it negative? Gravity's acting downward. Okay. In this class, you'll notice that we define these equations in feet per second rather than meters per second. So the constant for gravity is different because the unit is different. Do you remember what the constant for gravity is in feet per second? Okay, so it's negative 32. You would have used this formula many times in a physics class. Yep. What does t represent? Time in seconds. How about v sub 0? I pronounce that symbol as v naught. The initial velocity, very good. S naught would be, it's the initial height.
Long question. Thanks for pointing that out, James. Yeah, thanks. No problem. I didn't realize.
So we have a ship that's stranded in the ocean on top of the bridge, which is 80 feet above the ocean. A distress flare is shot straight up with an initial velocity of 72 feet per second. Provide a graph of the flare's height versus time and find the height after 1 second, 2 seconds, 4 seconds, and 5 seconds. That's what it said. That's okay. So we have two equations that we described or defined just a moment ago. We have S of t and we have v of t. Which one of the two equations are we interested in here? S of t, because S of t is for height, and we're asked for heights. Okay, so I want to graph a height versus time. So I need to fill in values for v naught and for s naught. What value are we going to put in for v naught? 72. And for s naught? 80. Okay. So now I'm going to graph this function on my calculator, and then I can also use my calculator to find those values. The directions on the problem asked me to graph it. Okay. So I'm going to go to my calculator. First thing I'll do is change my mode, because if I look at this function that I've written, I really just have two variables, right? I have s of t and then t. So I'm going to change the mode and turn it back into function mode from parametric. And then I'm just going to type in my equation exactly as it's written. Okay. Before I hit graph, though, I'm going to reset my window. So my variable x is representing t in this function. So I know time can't be negative, so my x min should probably be 0. And then I don't know how long this flare is going to be in the air. I don't know, maybe 5 seconds or something. You shoot a flare straight up, maybe it takes 5 seconds to land. I'm just guessing. The y scale, or the y min, again, y in this case is my s of t, so it's going to be a height. So 0 would be the minimum height. And then the maximum height, oh, I don't know, maybe that flare goes 200 feet up in the air. I'm just guessing. All I want to be able to do is see the picture, though. So let's hit graph and see how we did. Okay, that's not bad, but notice that I can't see where that ends at. So I'm just going to go back in and extend my x max. Maybe I'll pick 7, just so it goes a little bit further out so I can make sure where I can see where it crosses, so I can see the whole graph. Everybody okay with that picture? Okay, so if I want to find the height after 1 second, this is very easy to do with my calculator. I'm just going to press second and the trace command. From the calculate menu, I'm going to select the value option. Notice on the screen, the calculator is prompting me to pick a value for x. Well, I'm going to pick x to be 1. And that tells me that the y coordinate then is 136. So I know the height of the flare after 1 second is 136 feet. I can then just repeat that procedure 3 more times to fill in the rest of these. So I get 160 feet, and then 112 feet, and then 40 feet. Any questions about this? What I've just done there? What if I wanted to actually graph the actual path of the flare? Can I do this with my calculator in function mode? No, because I would need 3 variables, right? I need an x coordinate, a y coordinate, and then a time, right? So I can't do that in function mode. I can do that, though, in parametric. So I'm going to go ahead and go back to my menu and change my calculator to parametric mode. So the x coordinate, if I shoot the flare straight up and it falls straight back down, is the x coordinate ever changing? No, right? Since the flare's not moving left or right or any sideways direction. So I'm just going to pick the x value to be 1. You can really pick any number you want. I chose 1. The y coordinate is being described by the function we have here. So I'll just change that to negative 16t squared plus 72t plus 80. I'm going to go and reset my window here. So for the previous example, I used my time going from 0 to 7. My x, it doesn't really matter here, so let's just pick, say, 0 to 10. And then our y, we did 0 to 200. Okay, so let's go ahead and hit graph now. And what did we get? Just a straight vertical line. Does that make sense? Yeah, that's literally the path of the flare, right? We shot it straight up, and then it came straight back down. So, we started at 80 or whatever. The flare shot straight up, and it came straight back down and landed in the ocean. Everybody okay with that idea? Okay. So this is a pretty trivial example to bother with a parametric function on it, because there's literally no side-to-side motion. It's just all straight up and down. What if we had fired that flare at an angle instead? Now the x and y coordinates are both going to vary with time. And this is really what we mean more so in the case of projectile motion. So let's redefine these equations that we used before in a context in which we're launching something at an angle. Okay? It's a little less trivial than straight up and down. So those two sets of equations are x is equal to the magnitude of v times cosine theta times t. Y is equal to negative 16t squared plus the magnitude of v times sine theta times t plus s naught. The second set of equations, vx is equal to the magnitude of v times cosine theta, and vy is equal to negative 32t plus the magnitude of v times sine theta. Again, S naught represents the initial height of the object. So let's look at some examples here. Okay. So this example says you hit a baseball at 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence 300 feet away? If so, by how much? If not, where on the fence will it hit? So, which set of projectile motion equations do I need to use? The x and y or the vx, vy? X and y, because it's asking about heights of the ball, basically, right? Everybody agree with that? Because it's asking me is what will the ball's height be at this distance, basically, is what this question boils down to. Is everybody okay with that idea? Okay. All right, so these are the set of equations I'm going to use. What am I going to fill in for the magnitude of V? So go back to our definition, read again what the magnitude of V represents, if you're not sure. The initial velocity. So what's going to go in there? Great, 135. And what's going to go in place of theta? 16. And what's going to go in for S naught? 3. Is everybody okay with how we set up these two equations? So my plan is I want to figure out what the height of the ball is going to be after it's gone 300 feet. And I'm going to compare that to the 15-foot fence. Is everybody okay with that plan? In order to do that, though, I need to know how long the ball is going to be in the air, because the input for both x and y is time. Everybody's okay with that idea? So what I'm going to do is I'm going to use the x equation, putting up 300 in for x, and using that to solve for t. And then once I have that value for t, I can plug it into my y equation. To solve for the height of the ball. So when I type that all into my calculator, I get that y is about 3.51 feet. So did the ball clear the fence? What do you guys think? No. What happens instead? Okay, it hits the fence. How high up? About 3.51 feet above the ground. Everybody okay with that idea? Let's look at this situation on our calculator and visualize kind of what's happening, since we can draw the physical situation with our calculator in the parametric mode. So I'll go back to my parametric mode, and I'm going to type in my function exactly as it appears that I wrote above. So I'll do 135 times cosine 16 times t for my x, and then I'll do negative 16 t squared plus 135 times sine 16 times t plus 3. So that'll graph me the path of the ball. What I want to do also is I want to draw in the fence. Where is the fence located? What will be the x-coordinate of the fence? 300. And now the y-coordinates of the fence should be from 15 all the way down to 0, basically, right? I want that fence to extend all the way to the ground. Everybody agree with that? So the way that we're going to do that is I'm going to do 15 divided by the variable the variable t max. So I need to retrieve the variable t max. So to do that, I'm going to go to the vars menu. I'm going to go choose from the Windows option. I'm going to go over to the t/theta tab and select T max. and then put a t at the end. Window, and then over to the t/theta, and then choose t max. So now that I have that, I'm going to go ahead and try to graph this. To do that, I need to pick a window. So my baseball player's in the room.
Yeah.
A ball that's hit 300 feet is in the air for how long, would you estimate?
I don't know. 3.5 seconds.
Okay, so let's make that an overestimate, right? Just in case, because it doesn't do us any harm to overestimate, right? What we don't want to have to do is go back and change the window again if it's an underestimate. Yeah, I think 10 seems appropriate. So the x min should be 0. What should the x max be? We know it has to be bigger than some number. What number do we know it has to be bigger than? 300. So let's pick, say, 400. All right, now let's think about the height of this ball. The min should be 0. The ball's hit at a 16-degree angle above the horizontal. What kind of baseball, like what kind of a hit would you say that is? Pop fly? So like 16-degree angles like this. That's like a line drive, right? Does that get very high up in the air? No. So, I don't know, maybe I'll do 50 feet. Okay? So, used a little bit of common sense to try to pick these. So I hit graph. Oh, what happened here? Why didn't I get anything? Yeah, what's the issue? I should be in degree mode. All right. So there's the baseball, and there's my fence. Right? Notice the ball doesn't make it over the fence. Didn't hit a home run. Okay. Let's do this again. Stop clicking. All right. Second example. So it's same situation. I've just changed the information. So here the pitch was a little bit higher. We hit it at a little bit steeper angle, a little bit harder, but it's got to go way further and clear a much higher fence, right? What do we think? We gonna make it?
Possibility.
There's a possibility. It was kind of close last time, right?
Yeah.
All right, so let's start by just inputting these new values into our calculator and getting a look at the picture. So 141 is my new speed. 24 is my new angle. I'll just change some of these. And my new fence is 400 away and 20 feet high. We should probably change our window though again. So this time the ball's going 400 feet is where the fence is. So let's make that 500. And this time the ball's hit at a bit of a steeper angle. So maybe let's make that, let's make that Y max 100. So there's the ball, and there's my fence. What did we notice? Dingers, right? Well, let's figure out how much it made it over the fence by now, yes? Okay. So we're going to say that 400 is equal to 141 cosine 24 times t. So when we solve for t, we get t is 400 over 141 times cosine of 24. And we can use that to find the height of the ball at that time. So it's negative 16 times 400 over 141 cosine 24 squared plus 141 sine 24 times 400 over 141 cosine 24 plus 3.5. So when I type this all into my calculator, I get about 27.30 feet. So what does that mean? The ball clears the fence by how much? Not by 27 feet. The fence is 20 feet tall. So makes it over by 7.3 feet. Yeah. This guy smushed it pretty good, huh? Baseball aficionados. That's a pretty long way to hit a baseball. Oh, it was 400 feet over a 20-foot fence. It's pretty good, right? How far do you think that ball went? Assuming there's no obstructions, what do we need to do? Here, we're asking, if we're asking how far did it go, which are we looking for, X or Y? X, right? So we're going to have to solve Y to get the time to plug in for X, like the reverse idea of what we just did. So what should the height of the ball be at the end? Very good. So we'll solve the equation, negative 16t squared plus 141 sine 24t plus 3.5 equal to 0. What kind of an equation is this? Starts with a Q, quadratic. How would I solve a quadratic equation like this? I would use the quadratic formula. Yeah, you're not going to be able to factor this because one of our coefficients has a trig function in it. So that's likely not going to be real factorable. So t equals negative 141 sine 24 plus or minus the square root of 141 sine 24 squared minus 4 times negative 16 times 3.5 all over 2 times negative 16. So when I type this into my calculator, I get two results. Okay. Do both of these answers make sense? Do both of these answers make sense? No, what's wrong? Negative time doesn't make a lick of sense, right? So I don't want that one. This is the time that I want. What am I going to do with that? Yeah, I'm going to take my equation for x and plug that in to it. When I do that, I get 469.4 feet. So we knocked the stuffing out of that ball there, huh?
I say so. He's trying so hard. Very big fan.
All right, last question here for today. How far away could we place the fence and still have the ball clear that fence?
449.
You're just guessing. Let's figure it out exactly. So we're looking for an X or a Y here. Which one? How far is an X, right? That's a horizontal distance, right? So to find the value for X, we're going to need a T. We're going to get that T by solving the Y equation. What value are we going to plug in for Y? 20. That's the height of the fence, right? I want to figure out when the ball is, how far away can we place the fence so the ball can still get over it, right? This is the second example. You missed it. So this is a quadratic equation. In order to solve this, the first thing I want to do is subtract 20 from both sides so that it's equal to 0. And then just like before, we'll apply the quadratic formula.
Problems like these, how picky are you going to be about decimals?
If you round to 2 decimal places, you should be fine. Okay, so we get 2 answers from this. Which one do I want? Are they both reasonable?
Well, 3.2.
Yeah, they're both reasonable answers because they're both positive. The one we do want is the second one. Why did we get two answers?
Those intervals.
Think about physically what's happening.
Trying to find x, you can't really because it's the parabola, the y is going to be on 2 spots.
Right? Exactly. So the first value, the smaller value for t, is when the ball gets to 20 feet on its way up. And the second value for t is when the ball is at 20 feet on its way down. That's why we're getting two reasonable looking answers. You have to think a little bit about physically what's happening, though. Okay.
No, I didn't ask. I did not ask for this.
So what we got was the furthest home run we could have hit over the 20-foot fence was 421 feet and 0.07 away from wherever we were standing at the start of this. All right. What I would like for you guys to do for me for next time is, we're going to do 29 through 48.